All right, today we'll look at BJT characteristics and determining operating modes for a BJT transistor. All right, so we stopped right here. So these are the typical output characteristics for a BJT. Collector to emitter voltage on the x-axis and the collector current as a function of VCE. So IC as a function of VCE. And they are plotted as a set of curves for different inputs of the base current IB. So typically, the base current is measured in the microamps. So IB is typically in the microamps, which results in a collector current in the milliamps. Okay. So you can see, let's see. What happened here? All right. And I'm going to exaggerate this pose with a slight curve. And depending on the circuit configuration, this could be a flat line or it could have some slope. So I'm exaggerating this slope. This is almost flat for a common emitter configuration. Okay. So what does this mean? Well, for a specific IB value, meaning a base current of, let's say, 10 microamps or 20 microamps, the current would increase. For a very small increase in the voltage. Okay, after a certain point, right around here, it saturates at a value, and it behaves almost like a constant current source. So in this region, again, the slope is exaggerated. So it's almost like a flat line. So the collector current is almost flat. So for increasing voltages, the current remains almost flat, and so the BJT behaves like a constant current source. And we will use that in some of our models also. Okay. If we increase IB, then IC increases correspondingly. But again, it'll be a different set of curves, different set of data points. So for the same amount of VC, if IB increases, then IC also increases. And of course, the ratio of IC to IB is defined as beta, which is the current gain for a BJT. It's part of the spec sheet. And based on the characteristic performance, we have three regions: active, cutoff, and saturation. Okay, active, cutoff, and saturation. So this is typically defined as the active region, where you can see a small change in IB gives you a large output at the collector current. Cutoff region is like right here, where voltages and currents are typically zero or very, very small. And saturation is on the left, where the transistor is saturated, so The voltage is very small, but it's maximum value of current. Okay. Okay. So how do we determine the operating mode? Well, there's 4 modes. We talked about reverse active is something that we don't, we never use. It's kind of like a forbidden mode. That leaves forward active, cutoff, and saturation. So if we wish to determine the operating mode, we look at the voltages at the terminals. This is the collector, this is the base, and this is the emitter. The emitter base junction must be forward bias, meaning VBE must be a positive number. Okay, VBE must be a positive number. This is cut off, sorry. I'm talking about active. Got my slides mixed up. Excuse me. All right, so in cut off, both junctions are reverse bias. If both junctions are reverse bias, this is N, P, N. So the PN junctions must be reverse bias. Okay, so the N terminals must have a higher voltage than the P terminal, meaning the collector and emitter voltages must be higher than the base voltages. So VB is lower than both VC and VE. That would mean that the transistor is operating in the cutoff region. Okay, transistor is operating in the cutoff region. There is no current flow and we use this mode. As part of the switching, as part of the switching application, we say switch is off. Right? This is 1/2 of the BJT application as a switch. And we say that the switch is off. All right. Then we have saturation. In saturation, both junctions are forward bias. This is collector, this is the base, and this is the emitter. Meaning the base should be higher than both of them. And so if VC and VE are less than the base voltages, then the transistor is in saturation, and we'd say that the switch is on. Okay. And then that leaves active mode, which is what we discussed earlier. Active mode is when one junction is forward bias and the other junction is reverse bias. So an NPN transistor, the base emitter junction is forward bias, meaning base is higher than emitter. And since it is a forward bias PN junction, VB is equal to 0.6 or 0.7 volts. It's one diode voltage drop, 0.6 or 0.7 volts. In the active region, say amplifier. Now, we spoke about DC biasing, and now we're talking about different modes of operation. So how does it all work together? So let's say we are apply DC voltages to the three terminals, and we set the bias. Okay, bias in this particular regard simply refers to setting the operating mode of our transistor. Okay, setting the operating mode of our transistor. So let's say if we want or if we wish to use the transistor as an amplifier, we would model it or we would set the bias for the transistor to operate in the middle of the active region, right? Somewhere in the middle of the active region. And so our voltages, let's say they would have certain value. You would apply certain DC voltage, and then arrives a small AC signal at the base. And what that signal would do is it would shift the DC biasing voltages either towards the saturation or the cutoff regions. Okay. And let me make a small illustration. At VDC could be 10 volts, 15 volts, 20 volts. AC signal would be in millivolts or less than 1 volt. Okay. So the result of these two together gives us an amplified output. So this would be V in, and this is V out. Now, if our DC biasing voltages is not in the middle or the center of the active region, and it approaches saturation or it approaches cutoff, then the top half of our waveforms or the bottom half of our waveforms would be clipped. And we would say that the waveform or the output is now distorted. Okay, so the output would be clipped or distorted waveform. Okay, so our AC signal that arrives, it receives the power from the DC sources or the DC bias, and the output waveform could either shift towards the saturation region or it would move towards the cutoff region, depending on our biasing conditions and the input waveform. The top half could be clipped or the bottom half could be clipped, or both of them could be clipped. A real life example would be when you turn up the volume on any audio device that you have. If the speakers are unable to handle it, we hear a lot of noise, or we say it's distortion coming out from our speakers. So what is happening is we increased the volume or the amplification so much that the waveform is now large, and it cuts off at the top and it cuts off at the bottom. It results in distortion. Now, obviously, modern electronics are designed not to approach those levels. All right, let's take a pause. Let me know if you have any questions. Yes. We will see. So the question being asked is, how does this happen? And we will see that in just a few slides. We'll look at an example. We'll analyze using load line techniques, and we can see how it actually moves on the load line. Yes. Yes, we refer to it as being on. So cutoff and so question being asked is about the reference for the switch being on. And so, yes, if it's in saturation, we say transistor is on. If it's in cutoff, we say transistor is off. And those two modes put together is basically when we say we can operate the BJT as a switch. Yes. So the question being asked is about active mode. Actually, I was on active mode here. And so, yes, the base emitter junction must be forward bias. We can also do collector junction and forward bias. And so it'll be, that wouldn't work because the collector does not have as many free charge carriers as the emitter. The reason it works in one direction or only in that direction is because the emitter is very heavily doped. And because it's very heavily doped, doesn't have as many, so the collector is not as heavily doped as the emitter. It does not have that many free charge carriers. All right, common emitter configuration. So depending on the terminals and the configuration, we have three different modes of configurations. I'm going to quickly talk about all three of those. So BJT is a three-terminal device, right? And then FETs and MOSFETs are also three-terminal devices. So when you configure them, one of those terminals will be common to the input side and the output side. Okay. So if I draw the circuit this way, which terminal is common to the input and the output? Input and output. Collector, base, emitter. The emitter is common to the input and the output sides. And so this is known as a common emitter configuration, CE configuration. If the base is common to the input and the output, like this, then it's a CB configuration. And if the collector is common to the input and output, then we say it's a CC configuration. We simply flip this. CC configuration. Okay. For the most part, we'll only look at CE configurations. So typical circuit for a common emitter transistor will look like this. You apply a voltage here. This voltage is typically referred to as VCC. And here we would refer to as VBB. These would result in DC voltages appearing across the base emitter junctions and the collector emitter junctions. Input side is the base and emitter. So the base is referred to as the input terminal. So the input characteristic for a BJT would be a function of IB, would be a plot of IB as a function of the base emitter voltage VBE. And because it is a single PN junction that is forward bias, it is exactly the same as a diode, forward bias diode. And so plot this. looks like a forward bias PN junction diode. And then, of course, output characteristic is something we just saw on the previous few slides. It's IC, it's a plot of IC collector current as a function of VCE. So it's a set of curves, set of data plots of the values of IC collector current as a function of VCE. And since this is an NPN transistor, let's look at a PNP. So again, we won't do separate analysis of PNP because the analysis techniques and everything applies exactly the same. The only thing is voltage polarities and the current directions are now reversed. So the emitter current, instead of coming out, is now going into the terminal, right? It's PNP. Emitter terminal is now P-type, has excess of holes. Because it's excess of holes, the current is actually going in. Electrons are coming out. So the analysis is same as NPN. No different. So here, let's take a look at an example of a common emitter configuration for a PNP transistor. All the rules still apply the same. You have the emitter that is common. Here's the base, here's the collector current. But look at the supply voltages. Supply voltages are now flipped. So this is VCC and this is VBB. So polarities of the supply voltages are flipped. The current directions are also flipped. IB is no longer going in, IB is flowing out. Emitter current is actually flowing in. Characteristic, however, remains exactly the same. That doesn't change. Input current IB as a function of VBE still results in a diode, PN junction diode forward characteristic. And the output characteristic is still IC as a function of VCE. Let's take a pause. Let me know if you have any questions before we go into the examples. Yes. For which one? Oh, the input. It's the base emitter volt. It's a both characteristics are a plot of the current as a function of the voltage. On the input side is the base, so it's it's the base current IB right here as a function of the base emitter voltage VBE. And because the input side is a forward bias PN junction, the characteristic look exactly like a diode forward bias characteristic or a diode characteristic in the forward bias. And the output characteristic is a function of collector current as a function of, it's a plot of the collector current as a function of the collector emitter voltage, VCE. And then it's still exactly the same as a NPN transistor. Any other questions? So let's look at how we can determine the operating modes. So here's a summary. If both junctions are forward bias, it's in saturation, If both junctions are reverse bias, it's in cutoff. And if one junction is forward bias, meaning the base emitter junction and the collector base junction is reverse bias, then it's off. Diagrams here are for P and P. So these are P and P. These are NPN. So in the next few examples, we will determine what the voltages are at each of those terminals, and then we can reference them to this page or this slide and determine the operating modes. All right, let's take a look at example 1. So we have a circuit. It's rather straightforward here because the voltages are given to us. So if you want to determine the operating mode, you'd simply take a look at the voltages at the 3 terminals and make a logical conclusion. So VBB is given as 4 volts, VCC is given as 12 volts, V1, V2, and V3 values are all given to us. So V1 is 2 volts, meaning VB is 2 volts, VE is 1.3 volts, and VC or V3 is given as 4 volts, right? 3 voltages are given here. VE, VB, and VC. So determine the operating mode. What do you see before I go to the next slide? First, simply check the base emitter junction. If the base emitter junction is about 0.6 volts apart, see if base is higher than the emitter. If base is higher than the emitter by about 0.6 or 0.7 volts, it's forward bias. That's a forward bias diode voltage drop. So I'm going to take a look at VBE, and I determine that VBE is 0.7 volts. And if VBE is 0.7 volts, then it is forward bias. It is not in cutoff. There's only 2 options, right? There's 3 modes: cutoff, saturation, and active. If the base emitter junction is forward bias, it automatically means it's not cutoff, because cutoff requires both junctions to be reverse bias. So if base emitter is not in cutoff, that automatically, is not reverse bias, that automatically removes or eliminates one of the operating modes. So cutoff is gone. It could only be in active or in saturation. So that's your first check. Always look at the base emitter junction. And again, going back to that slide, summary slide right here. Right? Summary slide right here. If you look at the base emitter junction, which is right here, if it's reverse bias, then it's cut off. We don't need to do anything else. If it's forward bias, then you perform one more analysis, because now we have 2 more options. Okay. So here, I can see it's plus 0.7 volts. So it's not cut off. I need to perform one more analysis. If these 2 voltages were reversed, if VE was larger than VB, so for instance, if VE was equal to 2 volts and VB was equal to 1.3, then VBE would be equal to minus 0.7 volts. Could be any negative value, but the point would be that the base emitter junction is reverse bias. Then I would not need to do any other analysis. I would instantly state that it's in cutoff. Let's take a pause. Let me know if you have any questions. Yes. No, it's a closed switch. So a question being asked is, in saturation, it says it's a closed switch. In electrical terms, it's exactly the opposite of a mechanical valve. So electrical switch must be closed to permit current flow, and open switch would mean there's a break. So if it's cut off, it's open, and its saturation means it's permitting heavy current flow. It's closed. So it's on. So it's on and off. Yeah. So in those terms, an electrical switch is the exact opposite of a mechanical valve. And again, if VE is 2 volts or if it's higher, then it would be in cutoff. Okay. So then you would not need to do any further analysis. All right. So we establish that this is not in cutoff. So it must be either in active or in saturation mode. So let's test for saturation. See if the collector base junction is forward bias. So if collector base junction is forward bias, that means that collector must be higher than the base. And sorry, collector must be lower than the base. VB must be higher than VC, right? So if VB is higher than VC, I must obtain a positive number for VBC. So if I'm testing saturation mode for an NPN transistor, collector base junction must be forward biased, meaning VB must be larger than VC. Right? NPN, base must be higher than collector and emitter. Voltages, VB is 2 volts, VC is 4 volts, results in VBC as minus 2 volts. Negative number, hence reverse bias. And if it's reverse bias, it's not in saturation. That leaves only active mode. And automatically, we also know NPN transistor, collector base junction is reverse bias, and it's active mode. Make sense? Yes. So let's see if I understand you correctly. Forward active, is that what you mean? So this is forward active mode. So, oh, previously you mean in the previous one here? Both of them are reverse bias. Is that the mode that you're asking? Okay, so the question being asked is, would there be reverse mode in both junctions? But both junctions are reverse bias, it'll still be off. So the question being asked is whether we need to check the other junction if the first junction is cut off and reverse bias. The answer is no, because if one junction is reverse, if the emitter base junction is reverse bias, it doesn't matter what happens at the other junction. The other junction could be forward bias, could be reverse bias, it's still being cut off. Good question, good point. So if this is reverse bias, it doesn't matter what the collector base junction does. Collector base junction could be forward bias, it could be reverse bias. It makes no difference. Transistor is cut off because the large amount of carriers are present in the emitter. If it's reverse bias, they are not going anywhere. Make sense? Neither junction, it's not going anywhere. Okay. Other questions? Other questions? Okay. So that only leaves active mode. Excuse me. There is another way to check for saturation, and that is if we check VCE is less than 0.4 volts. So in typical saturation mode, VCE would be very, very small. So we look at the characteristic curves. Actually, rather than drawing it, let me just go back. Oh, there we go. That's the slide. Right here. Current would be high for any given IB values. Look at the values of the voltage. VCE would be very, very small, right around here. So if a transistor is in saturation, VCE is less than 0.4 volts. Typically, it's like 0.2 or 0.3 volts. The VCE, collector to emitter voltage, is very small. That's an indicator that the transistor is in saturation. So we can also check for value of VCE, whether it's less than 0.4 volts. Here, VCE is 2.7, and so that means it's not in saturation. Just a different kind of check. Okay. This is about the typical value. Or BJT in saturation. 0.2 to 0.4 volts. Really less than 0.4 volts. All right, so let's look at an example for a load line analysis or a CE amplifier. Okay. So here is the circuit, and we are given the input and the output characteristic curves. VCC is given here, and VBB is given here. And the values, let's see what value I have. Oh, values will come later. Right now, we simply outline the procedure. This plus this gives me the biasing conditions. So VCC and VBB set biasing conditions, or basically operating points for the BJT. So think back to the diode as well as the Zener diode. We perform analysis on the diode using load line techniques. What do? We isolate the circuit and we apply KVL around the loop to generate our equations. And we determine the coordinates of the two endpoints, and then we plot the line that intersects the curves, the diode characteristic curves at a certain point. That intersection point is the solution of the load line and gives us the operating point for the diode. So we'll perform the exact same thing for a BJT. We will apply KVL on the input side. We will apply KVL on the output side. We will generate an equation for a line. We'll determine the two endpoints of those lines. We'll plot them on the input and the output side. Two different analyses, of course. And then the intersection point of those load lines with the characteristic that is provided to us gives us the operating point of the transistor. So the input side, we'd have one intersection On the output side, we would have a intersection, but the output side will move in response to any AC signal that's applied on the input. So this would be the DC operating point right here. And that operating point would move up or down depending on the applied AC signal. And that will come later on in the example. So input side is the base and the output side is the collector. Okay, base current and voltage and collector current and voltage. What else do we notice? IB plot is given to us and IB values are given to us here, 10 microamps to 50 microamps, and makes things rather simple or straightforward. If you look at IC, IC is 1 milliamp for a input current IB of 10 microamps. That makes it rather straightforward to find the current gain beta, which is IC over IB. So 1 milli divided by 10 micro gives me a beta value of 100. Okay. Far so good. Let's apply KVL and generate our equations. So on the input side, like KVL on the input side, and I have this right here. How many voltages do we have? We have V in of T. We have the voltage drop across RB. We have VBE, and we have VBB, 4 voltages, right? So if I write my KVL expression, I would get minus V in of T plus VRB plus VBE minus VBB is equal to 0. And this is just my preferred way of applying KVL. You can apply KVL however you are comfortable with. And I can replace, if I rearrange the terms, I get V in of T plus VBB is equal to IB times RB plus VBE. Okay. Now, these 3 quantities are known values. VBB is a supply voltage we apply at the base terminal. RB is the resistor, and V in of T is the AC input signal. So all 3 of those are known. The only unknowns are IB and VBE. So 2 unknowns. Same thing as the diode load line. We have 2 unknowns, diode voltage and diode current. If you want to plot a line, that line must intersect the X and Y axes at some point, meaning at that value, the axis value is either X is equal to 0 or Y is equal to 0. So we can plot if VBE is equal to 0, then IB is equal to VBB plus Vin divided by RB. And if IB is equal to 0, then VBE is equal to VBB plus Vin. And that's the input equations. So far, it's still the same as a forward bias. I mean, not forward bias, but so far as the load line analysis for a diode. Okay. On the output side, once I apply KVL, I have only 3 voltages: VCE, ICRC, and VCC. So I would get minus VCE minus VRC plus VCC is equal to 0. Can rearrange the terms, and I can get VCC is equal to VCE plus VRC. And to determine the 2 intersection points, if IC is equal to 0, actually VRC should be ICRC. If IC is equal to 0, then VCE is equal to VCC. And if VCE is equal to 0, then IC is equal to VCC over RC. All right, let's take a look at it. So we applied input we applied KVL on the input side, 4 voltages. We replace the voltage across the resistor in terms of the current and the resistor. So IB times RB gives us the VRB values. Plug in VBE and IB is equal to 0. In turn, we find equations for IB and VBE. If we do not apply any AC input, then Vin of T is equal to 0. It will simply be the biasing point or the operating point, right? If Vin of T is equal to 0, we would say it's simply the bias point, meaning the Q point is fixed. Q point is fixed. And once you plot the line, this is that Q point. It's not going to move. But if you apply an AC input signal, now Vin of T has some value. Some sort of sinusoidal waveform. And this Q point moves up and down the characteristic curve. That Q point will move up or down, meaning VBE and IB will change in response to the applied input, AC input. And because IB is changing, IC will correspondingly change on the output side. And we will see that in next class on Friday. Okay, we'll see that in next class on Friday. How is the input transferred to the output? Okay. And we will see how a small input current IB results in a large output current IC. All right. So we'll end class here today and we'll pick up here again on Friday. Friday quiz based on the previous 3 classes. Homework is also updated